In November of 2012, a NASA spacecraft slipped out of the bubble that has surrounded our solar system since before the first humans stood upright. Nobody heard it happen. There was no flash, no boundary marker, no signal telling ground control the exact moment it crossed over. And then, 5 years later, something strange started coming through Voyager 1's instruments. Not silence, which is what almost every scientist expected from the space between stars. A sound, faint, steady, and completely unexplained. A tone rising from a region of the universe that was supposed to be close to empty. It has not stopped since. Think about where this spacecraft actually is. 14 billion miles from home. Past every planet, past the last outpost of the sun's influence, in a region of space so far removed from anything familiar that light itself needs. The better part of a day to cross the distance between Voyager and Mission Control. And out there, in a place that generations of physicists described as close to nothing, an instrument built with 1970s electronics keeps picking up a signal that shouldn't exist. What Voyager found out there wasn't just a sound with no clear source. It was a sign that the space beyond our sun is thicker, stranger, and more structured than any model predicted before we actually sent something to go and check. And the deeper the spacecraft has traveled, the stranger the readings have gotten. Scientists still don't have a complete explanation. What they do have is a spacecraft, older than most of its own engineers, quietly recording something that shouldn't be there. To understand why this matters, you have to understand what interstellar space was supposed to be like, according to everything we thought we knew before Voyager 1 actually got there. For most of the 20th century, the region beyond the solar system was treated, scientifically, as close to a vacuum. Not a true vacuum, but near enough that most models simplified it that way. A few atoms per cubic meter, drifting cold and largely undisturbed, left over from the deaths of stars that exploded long before our sun ever formed. Quiet, by definition. That was the assumption baked into decades of astrophysics. Voyager 1 was never built to test that assumption directly. It launched in 1977 with a much more immediate job: fly past Jupiter and Saturn, photograph their moons, and take advantage of a rare planetary alignment that happens roughly once every 176 years. It succeeded beyond anything NASA had hoped for. It gave humanity the first real look at Jupiter's moon Io, a volcanic world that shouldn't have been geologically active at all, and it swept past Saturn's moon Titan, revealing a thick, hazy nitrogen atmosphere unlike anything else in the solar system. That was supposed to be the whole story. Fly by the giants, send back a few years of unprecedented images, and let the spacecraft coast into irrelevance. Instead, Voyager 1 kept going, and going. For over 4.5 decades now, it has continued outward, carrying instruments that were never expected to still be, functioning this long, powered by a plutonium generator that loses a little output every year. By 2012, it had traveled roughly 18 billion kilometers from the sun, far enough to reach the outer edge of what scientists call the heliosphere, the vast bubble of charged particles, and magnetic field lines blown outward by the sun itself, extending far past every planet in the solar system, including Pluto. The edge of that bubble is called the heliopause. It is the place where the pressure of the solar wind, the constant stream of particles our sun throws outward, finally gives way to the pressure of the interstellar medium, the thin material that fills the space between stars. Crossing it means leaving the sun's direct influence behind entirely for the first time in the history of any spacecraft, any probe, any human-made object. Voyager 1 made that crossing quietly. There was no dramatic jolt, no visible line to cross. Scientists confirmed it happened only after the fact, using indirect evidence because the instrument best suited to measure the plasma density directly, the plasma science instrument, had stopped working years earlier. Voyager 1 became the first human-made object in interstellar space, and for a while it had almost no way of directly telling anyone what it was actually flying through. By the time Voyager 1 reached the heliopause, the instrument best equipped to measure plasma density directly had already been dead for years. It had failed back in 1980, decades before anyone needed it for this. So when the spacecraft actually crossed into interstellar space, scientists on the ground had no clean, immediate way to confirm the density of what surrounded it. They had theories. They had models built from decades of indirect observation, radio astronomy, and educated extrapolation. What they didn't have was a direct measurement. Not yet. That's where the story gets strange. In April of 2013, something happened on the sun. A coronal mass ejection, a massive burst of charged particles hurled outward during a solar storm, rippled through the solar system, and eventually reached Voyager 1, more than a year after leaving the sun. When that shockwave hit the plasma surrounding the spacecraft, it caused the plasma to oscillate, to vibrate, at a specific, measurable frequency. And Voyager's plasma wave instrument, one of the few still functioning, picked it up. That single event let scientists calculate the density of the plasma around the spacecraft directly, for the first time since it left the solar system. And the number they got back didn't match the models. The interstellar medium out there wasn't as thin as decades of theory had predicted. It was roughly 40 times denser than what Voyager measured just before crossing the heliopause, which was expected, since the interstellar medium really is generally denser than the tenuous solar wind way out at the edge of our bubble. But even accounting for that, the specific density readings were higher than pre-Voyager models of interstellar space had anticipated. Not by a small margin, either. Enough that scientists had to start reconsidering some basic assumptions about what fills the space between the stars. Then, in 2017, something happened that nobody had a clean explanation for. There hadn't been a major solar storm to trigger it, no obvious shockwave rolling out from the sun. And yet, Voyager's plasma instrument picked up oscillations again. Fainter this time, but real. A persistent hum present in the data, showing them up again and again over the following months and then years. Researchers at the University of Iowa, working with Voyager's original plasma wave instrument, spent time analyzing this ongoing signal and confirmed what it looked like. Continuous, low-level plasma oscillations, without a clear triggering event. Not a one-time echo of a solar storm, something closer to a background hum, sustained in a place that was supposed to be close to silent. That's the moment the story stopped being about a single strange measurement and started being about an ongoing mystery that Voyager has now been recording for years, one that scientists are still working to fully explain. So what is actually causing it? And why does interstellar space seem to be so much more active than anyone expected before we sent something out there to listen? The plasma wave. The instrument on Voyager 1 wasn't designed to be a microphone in any literal sense. It measures oscillations in the electric field, caused by charged particles vibrating at specific frequencies. Scientists convert that data into an audio range, so human ears can process it, which is why you'll sometimes hear this described loosely as Voyager hearing a hum. It's not sound the way sound travels through air, because there's essentially no air out there to carry it. It's a signature of plasma density, translated into something we can listen to. And what that signature has been telling researchers, consistently since 2017, is that the plasma in interstellar space near Voyager 1 isn't static. It's oscillating in a low, persistent way that doesn't require a dramatic external trigger like a solar storm to sustain itself. One explanation researchers have proposed is that the interstellar medium itself is turbulent on small scales, more dynamic than the older simplified picture of a calm, mostly undisturbed sea of particles. Turbulence in plasma can generate these kinds of low-level oscillations naturally, the way currents and eddies churn water even without a storm overhead. If that's what's happening, it means the space between stars has more internal structure and motion than most 20th century models accounted for. It's worth pausing on how strange that idea actually is once you sit with it. Interstellar space, in the older textbook description, was supposed to be close to inert, a few particles per cubic meter, drifting with no meaningful internal activity, cold and largely undisturbed on human timescales. A background hum implies motion, it implies the medium itself is doing something, constantly, without needing a solar storm to kick it into action. That's a fundamentally different picture than the one most physicists carried into the Voyager mission. But the hum wasn't the only surprise. As Voyager 1 continued moving deeper into interstellar space over the following years, additional shock events from the sun, rippling outward the same way the 2013 storm did, let scientists recalculate the plasma density again and again. And the trend that emerged was almost as strange as the hum itself. The density kept increasing, not staying flat, not fluctuating randomly around some fixed number, but rising the farther Voyager traveled from the heliopause. By the early 2020s, measurements showed the plasma density around the spacecraft had climbed well beyond what it had been just after the 2012 crossing, in some cases described by researchers as roughly double the earlier readings, even though Voyager was now traveling through territory that should, according to older models, have been thinning out, not thickening. That's a genuine problem for the old assumption of a smooth, roughly uniform interstellar medium. If the density were simply constant out there, moving farther from the sun shouldn't produce a steady climb in the numbers. Something in the structure of the local interstellar environment is uneven. Voyager appeared to be moving through a region where the material genuinely gets denser as it goes, not thinner. Then came a second puzzle, one that had nothing to do with density at all. It involved the magnetic field. Before Voyager 1 crossed the heliopause, scientists expected the direction of the magnetic field to change noticeably. Inside the heliosphere, the field is shaped by the sun's rotation and the outward flow of the solar wind. Outside it, in true interstellar space, the field should be shaped by entirely different forces, tied to the broader structure of the galaxy rather than our star. A meaningful shift in direction seemed like the obvious signature that Voyager had truly left the sun's domain behind. Instead, when Voyager 1 crossed over, the magnetic field direction barely changed at all. The orientation on the interstellar side of the heliopause was, within a small margin, nearly the same as it had been just inside it. That result confused scientists at the time, and honestly, it still does. If the interstellar magnetic field lined up almost seamlessly with the heliosphere's own field at the boundary, it raises questions about how sharply defined that boundary really is, and whether the sun's magnetic influence extends its shape further into interstellar space than anyone had modeled. Scientists have floated a few different explanations for all of this, and it's worth being honest that none of them are fully settled yet. One idea centers on something called the local bubble, a vast, roughly hourglass-shaped cavity in the interstellar medium, carved out an estimated 14 million years ago by a series of supernova explosions from massive stars that used to occupy this part of the galaxy. Our entire solar system happens to sit inside this bubble right now, drifting through material that was violently reshaped by those ancient blasts. If Voyager's density and magnetic field puzzles are connected to the structure of the local bubble, that would mean the spacecraft isn't sampling some generic textbook patch of interstellar space at all. It's sampling the leftover architecture of stellar explosions that predate human civilization by millions of years, still shaping the immediate galactic neighborhood the sun happens to be passing through. Another possibility is more localized. Some researchers have suggested Voyager may be passing through the outer edge of the heliosphere's own influence for longer than expected, a kind of transitional zone where solar and interstellar material blend and interact, rather than switching over cleanly at a single boundary. Under that idea, the strange readings wouldn't represent deep interstellar space at all, but a messy extended handoff zone that older models never accounted for. And there's a third, more unsettling possibility, one scientists raise more cautiously, that our understanding of the broader interstellar medium, beyond just the region immediately around the solar system, is simply incomplete. That the assumption of a calm, mostly uniform thin plasma between stars was built on theory and indirect observation, because until Voyager, nobody had ever actually been there to check. Now that something finally has, the numbers don't match the old picture, and there's no way to know yet whether that's a local anomaly, tied to our unique position inside the local bubble, or a sign that interstellar space in general is more textured and dynamic than astronomers assumed for most of the 20th century. None of these explanations cancel each other out, either. It's entirely possible that all three are true at once, layered on top of each other. A messy transitional boundary sitting inside a supernova-carved cavity, embedded within a wider interstellar medium that turns out to be more turbulent than the smooth, idealized version found in older textbooks, untangling which effect is responsible for which piece of the data is exactly the kind of problem that requires more measurements over more time, for more locations, which is precisely what a single aging spacecraft, or even two, struggles to provide on its own. The reason scientists take these readings seriously, rather than dismissing them as instrument error or a fluke of one aging spacecraft, comes down to a second data point that arrived a few years later. Voyager 2, Voyager 1's twin, launched just weeks earlier in 1977, but sent on a different trajectory, one that eventually took it past Uranus and Neptune before it too began heading toward the edge of the solar system. It crossed the heliopause in 2018, 6 years after its sibling, in a completely different direction through space. And critically, Voyager 2 still had a functioning plasma instrument at the time, the one that had failed on Voyager 1 years before Voyager 1 even reached the boundary. That meant Voyager 2 could measure the interstellar plasma density directly, immediately, without waiting for a solar storm to trigger an oscillation. The results lined up with what Voyager 1 had found. Elevated plasma density, higher than pre-Voyager models predicted, measured independently by a different spacecraft, moving through a different region of space, years apart from its twin. That's what turned this from a single strange anomaly into a pattern, worth taking seriously. Two spacecraft, launched decades ago with 1970s technology, heading in different directions, both reporting the same basic story. Interstellar space right around our solar system is denser and more structurally complicated than the models assumed. There's a certain irony in that. The instrument confirming these strange readings on Voyager 2 is one that failed on its twin decades earlier, for reasons engineers never fully resolved. If Voyager 1's plasma instrument had survived, we might have had direct density measurements from the very moment it crossed the heliopause in 2012, instead of waiting for a solar storm to trigger an indirect calculation the following year. Sometimes, the biggest scientific confirmations come down to which piece of 45-year-old hardware happened to still be working when it mattered most. Which raises the deeper question underneath all of this. If the space just outside our solar system is this textured, this active, This shaped by ancient stellar violence, we can still detect the fingerprints of what does that mean for how we picture the wider galaxy beyond it. For a long time, the interstellar medium was treated almost like a placeholder in astrophysics, something that existed in the gaps between the objects astronomers actually cared about: stars, planets, nebulae, galaxies. A background, not a subject. Voyager's data is quietly pushing back against that. The region immediately surrounding our solar system isn't a blank canvas. It's the scarred, restructured remnant of supernovae that detonated millions of years before anything resembling a human walked the Earth. We are, right now, moving through the aftermath of violence that predates our species entirely, and the two most distant spacecraft humanity has ever built are the only instruments that have ever measured it directly. Consider what that actually means for the sun's place in the galaxy. The local bubble isn't some isolated curiosity, sealed off from everything else. Astronomers have mapped its rough shape using data from other missions, including surveys of nearby young stars that appear to sit along its walls, formed from gas that got compressed when the ancient supernova shockwaves swept through the region. The sun happens to be drifting through the middle of it right now, and has been for a long stretch of its orbit around the galactic center. Voyager isn't just measuring space, it's measuring the specific scarred neighborhood our star happens to be, passing through at this exact point in its multi-hundred-million-year orbit. A few million years earlier or later, and the readings might look completely different. There's also a more immediate, almost bittersweet layer to this story. Voyager 1 and Voyager 2 are not going to be able to keep sending back this data forever. Both spacecraft run on radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity, and that power supply shrinks a little every single year. NASA's engineering teams have spent the past several years making increasingly difficult choices about which instruments to keep running and which to shut down, trying to stretch the mission for as long as scientifically possible. Instruments have already been powered off, one by one, to conserve what energy remains. Engineers have even attempted a fix, nicknamed internally as the Big Bang, an effort to free up additional power and potentially bring some capability back online, buying the mission more time before the lights finally go out for good. Sometime around mid to late November of 2026, Voyager 1 is set to cross another milestone, one that has nothing to do with plasma density or magnetic fields. It will become the first human-made object to reach a full light day from Earth, a distance so vast that a radio command sent from Mission Control will take 24 hours just to arrive. And any reply, if the spacecraft is even able to send one by then, will take another full day to come back. It is a distance that makes real-time conversation with a spacecraft, in any meaningful sense, essentially impossible. We are talking to something that answers a day later, from a place that keeps rewriting what we thought we knew about the space between the stars. Every year that passes narrows the window scientists have to keep listening to that hum, keep tracking that rising density, keep trying to understand what it means before the power finally runs too low. And Voyager falls silent for good. There is no successor mission currently in flight to pick up where Voyager leaves off. No second-generation interstellar probe is out there right now, quietly following the same trajectory with better instruments and a longer power budget. Concepts exist on paper, proposals discussed within the scientific community for a dedicated interstellar probe designed from the ground up for this kind of work, but nothing has launched. When Voyager 1 and Voyager 2 finally go dark, whenever that ends up being, humanity will lose its only direct, real-time window into this part of the galaxy, possibly for decades, possibly longer, until something new is built, funded, and sent on a multi-decade journey to catch up to where these two machines already are. So what do we actually know, and what remains a mystery? We know Voyager 1 detected persistent, unexplained plasma oscillations in interstellar space, beginning in 2017 without a clear solar trigger, and that this hum has continued to appear in the data in the years since. We know the plasma density measured around both Voyager spacecraft, independently in different regions of space, is higher than pre-Voyager models of the interstellar medium predicted, and that it appears to have continued rising as Voyager 1 moves farther from the heliopause. We know the magnetic field direction barely shifted across the heliopause boundary, a result that still doesn't fully match theoretical expectations. And we know our solar system sits inside the local bubble, a cavity shaped by ancient supernovae, which may explain some or all of what Voyager is finding, though that connection isn't fully confirmed. What we don't know, not yet, is the complete picture. Whether this is a local quirk of our specific neighborhood in the galaxy, carved by explosions that happened long before recorded human history, or a sign that interstellar space in general behaves in ways our models simply failed to anticipate, because until 1977, nothing built by human hands had ever traveled far enough to check. There's something worth sitting with in that. Two machines, designed in the early 1970s with less computing power than a modern calculator, carrying gold-plated records etched with the sounds of Earth, greetings in dozens of languages, whale song, a heartbeat, drifting outward on a one-way trip with no return, no maintenance, no upgrades. They were never supposed to still be talking to us. Their planned mission ended at Saturn. Everything since then, every year of interstellar data, every strange reading, every unexplained hum, has been borrowed time, squeezed out of hardware that engineers in the 1970s hoped might survive a few extra years past the outer planets, at best. And after everything, after the flybys, the historic images, the decades of silence from a dying power source, it's still teaching us something new, reminding us that the space between the stars was never actually empty. It was just unmeasured. Nobody had gone far enough to check, so the models filled the gap with the simplest assumption available: nothing. Much going on out there. Voyager quietly proved that assumption wrong, not with a dramatic announcement, but with a low, persistent signal that kept showing up in the data year after year, refusing to be explained away as noise, somewhere out past the edge of the sun's influence, moving through the reshaped remains of stars that exploded before the first humans existed. A machine we built is still listening, and for now, before the last transmission finally goes quiet, something out there beyond our solar system is humming back at us,